Remember that what I mean by symmetries is the way that you can take this triangle out of the box and fit it back again. For example, we could rotate it through 2 pi by 3, like that. Or, if we take it back to its original position, another possibility would be to flip it about this vertical axis, like that. You probably remember that there were 6 of these symmetries in all. There were 2 rotations, we call those R1 and R2, and 3 flips about each of the axes. We'll call those ones F1, F2, and F3. And then, of course, there's the identity, which just corresponds to doing nothing. You may remember as well that you can combine these symmetries by performing them successively, one after the other. And what you get is a group. But what's all this got to do with linear transformations? Well, the point is that you can regard this triangle as lying in a plane. And then, if you actually rotate the plane, for example, suppose you rotated the plane through 2 pi by 3, then the triangle will rotate as well with the plane and eventually end up in exactly the same situation that it was to start with. So in that way, we can think of the symmetry as a linear transformation. And you can do exactly the same thing for all the other symmetries. Each of the 6 symmetries you can think of as linear transformations of the plane. Now, we know that we can represent linear transformations by matrices. And we also know, as I said earlier, that the 6 symmetries form a group. So the question arises, can we put this arrow in across here? In other words, does this set of matrices form a group? Well, if it's going to form a group, then we need to ask 2 questions. What's the group operation? How do we combine the matrices? And what are the inverses of the matrices in this group? First of all, let's specify the particular matrices for the particular symmetries of the triangle. Here's Robin.
Well, you've already seen how to work out matrices in the first section of the text. But just let me quickly remind you how it goes. We start off by taking 2 basis vectors. We work out their images under the transformation. And these images we put as the columns of the matrix. So, for example, if we've got the standard basis like this, then we work out the image of 1, 0. That's PQ, for example. And PQ goes in the first column of the matrix. And similarly, we work out the image of 0, 1. If that's RS, then RS becomes the second column of the matrix. Let's now try this with the symmetries of the triangle. We'll flip the triangle about the vertical axis. Watch what happens to the basis vectors. Now let's calculate the matrix. Start with the first column. That's the image of the first basis vector. Now for the second column. That's the image of the second basis vector, which hasn't moved. So this is the matrix corresponding to a flip about the vertical axis. Now we'll look at a different symmetry, a rotation through 2 pi by 3. This time, the image of the first basis vector is cos 2 pi by 3 sine 2 pi by 3. That is, minus a half root 3. And this is the image of the second basis vector. Finally, we'll look at the identity symmetry, the one that leaves the triangle in its original position. Both basis vectors stay where they are. So here are the matrices for the three symmetries we've just looked at. Here's the matrix corresponding to the vertical flip, the matrix for the rotation, and the identity matrix for the identity transformation. And as you can see, I've got the matrices for the other three symmetries as well. So what we've got are 6 symmetries and 6 matrices. Well, that's all very well, but what are we going to use these matrices for? The important thing about matrices is that we can use them to do calculations. If we've got a matrix, we can calculate the image of any vector just by using matrices. In fact, we do it by using the dot product rule. If this is my vector, and this is the matrix, then we can calculate the coordinates of the image by using dot products. So to find the first coordinate, we dot the first row of the matrix with the vector, and their dot product is AX plus BY. And similarly, to find the second coordinate of the image, we take the second row and dot it with the vector to give us CX plus DY. So these are the coordinates of the image vector. Let's now look at this geometrically. Look at the vector 2, 1. What happens when we flip it about the vertical axis? We get minus 2, 1. But how does the matrix tell us that? We'll apply the dot product rule. Dot the first row with the vector, minus 1 times 2 plus 0 times 1. That's minus 2. And now the second row. The answer is what we'd expect. Minus 2, 1. Now with that flip, we can see what the image vector is going to be. But what happens if instead we take a rotation by 2 pi by 3? This time, it's more difficult to guess the image vector, but we can easily use the matrix to work it out. Dot the first row with the vector, and now the second row, and that gives us the image vector. So that's how we can use a matrix to find the image of a vector. And in fact, it works in general. We can use it for any matrix and for any vector.
So corresponding to each symmetry of the triangle, we've got a matrix, and we can use that matrix to actually calculate what happens to any particular point under one of these transformations. But that's only half the story, you see, because remember that we can combine these symmetries by performing them one after the other. And what we're after is the corresponding way of combining the matrices. So to get at that method of combination, let's just follow through a particular example. Let's take 2 symmetries. Let's first of all take, say, F1. That's the flip about this axis. And follow that by R1, the rotation through 2 pi by 3. We end up, of course, with another one of the symmetries. Which one? Well, if you look at this C down here, you'll see that this vertex is exactly the same position as it started in. And so we must have ended up with a flip about that axis. That's the flip F3. Let's see what that looks like in symbols. Well, if we take any point x in the triangle and use F1 and then R1, we end up with this point, R1 of F1x. And we've just seen that that is the same as F3x. And what we've got to do is to interpret that in terms of matrices. Well, we've seen that the matrix corresponding to F1 is this matrix. And this matrix corresponds to R1. And F3 is represented by this matrix. In other words, the combination of these two matrices produces this matrix. Well, that's all very well. We know which combination produces which matrix, but we still don't know the law of combination. We still don't know how to apply this to any two matrices. And the key to tackling that one is, once again, to think of the symmetries in terms of linear transformations. And why? Because we know how to represent a linear transformation by a matrix, so we can interpret these matrices in that way. For example, suppose we want to look at the first column of this matrix. How do we work it out? It's just the image of the first basis vector. So that column is just the image of the first basis vector. So if we follow through what happens to the first basis vector under these two transformations, we'll be able to find out how to calculate that column. Well, what happens to the first basis vector under the first symmetry? It just gets mapped to the first column of that matrix. And how do we work out what happens to that vector under the second transformation? Well, we just operate with this matrix on that vector in the usual way. So operating with that matrix on that vector must produce this first column, because both are just the image of the first basis vector. And exactly the same thing applies to the second columns. Operate with that matrix on that second column will give you that second column. So that's given us our law of combination. All we have to do is to operate with matrices on vectors in the usual way.
So what we do is to use the dot product rule again. If we want to find the top left-hand entry of the product matrix, we dot the top row with the left-hand column. And that gives us AP plus BR. And we can do the same for the other entries. For the top right-hand entry, we take the top row and the right-hand column and dot them. For the bottom left-hand one, we take the bottom row and the left-hand column. And for the bottom right entry, we take the bottom row and the right-hand column. Let's now try this for our symmetry matrices. We started with a flip about the vertical axis. And this was its matrix. Then we rotated by 2 pi by 3 with this matrix. Now we'll use the product rule to work out the resulting matrix. Top left-hand element, bottom left-hand element. That gives us the left-hand column of the product matrix. Now the top right-hand element. Bottom right-hand element. And that's the rest of the product matrix. You may have wondered why we always use the rows of this matrix and the columns of this one. Why not the other way around? Well, the point is, of course, that these matrices represent symmetries. And you can't combine symmetries the wrong way around, and so you can't combine the matrices the wrong way around either. Or in other words, matrix multiplication is not commutative.
So that's our question answered. We can multiply matrices in a way which corresponds to the way that we combine symmetries. And we know that symmetries form a group. So now we know that our set of matrices will form a group, and I can take off the question mark. But let's widen this question a little bit. You see, here we've only got 6 symmetries, 6 matrices forming a group. But we can construct any number of 2 by 2 matrices. And so it seems a natural question to ask whether perhaps the complete set, the whole set of all 2 by 2 matrices might form a group. Well, to tackle that one, let's look at the group axioms once again and check them through. First of all, closure. Well, there's no problem there at all, because 2 by 2 matrices multiplied together will just give us another one, and so that's certainly closed. Associativity, well, we could actually multiply those 2 matrices together, see what we get, then multiply by that, and then we could pair those together, multiply them, multiply by that, and see if we get the same answer. But that's a bit tedious. It's far more interesting to notice that these matrices represent linear transformations, and multiplication represents composition of transformations, and that's composition of functions, which we already know is associative. So we certainly have associativity for matrices. Identity, fine. This is the identity matrix, and that's certainly a 2 by 2 identity element for our group. What about inverses? Well, we know that our set of 6 matrices had inverses. They must have done because we had a group. But remember now that we've widened the question, we're considering all possible 2 by 2 matrices. And we're asking the question, does any 2 by 2 matrix have an inverse? Well, what about this one? Now that matrix can't possibly have an inverse. Why? Because if you multiply that by any other matrix, you'll just get this back again. You'll just get a matrix with 0, 0, 0, 0. There's no way that you can multiply that by another matrix to give you the identity as you would want for its inverse. Well, of course, that matrix is a bit special, but unfortunately, there are a lot of other matrices which are not quite as special as that one, which don't have inverses. So it looks as though we're in quite deep trouble. But can we salvage anything from the situation? Well, we could if we could find a test for whether or not a matrix had an inverse.
Well, there are several ways of testing whether or not a matrix has an inverse. We're first of all going to do it geometrically. Suppose the transformation rotates the plane through a certain angle, say pi by 4. Then the inverse transformation rotates it through minus pi by 4. And this is the inverse matrix. But what about a different transformation? For example, this one. The images of the 2 basis vectors are the same. And that means there's no inverse. Because if there were, would the image vector go back to here or to here? Well, the second transformation didn't have an inverse because it collapsed the basis vectors together. And so the corresponding matrix won't have an inverse either. But what happens in general? Supposing we have a general matrix, A, B, C, D. How can we test whether this has an inverse? What we do is look at the number AD minus BC. That's A times D minus B times C. In this case here, 1 times 1 minus 1 times 1 is 0. But for this one, this times this minus this times this turns out to be 1. So here it's 0, and here it's not 0. Well, why is that important? Well, the answer lies in the geometry of the transformation. So let's take these away. And remember that if we have a transformation which does have an inverse, then the images of the basis vectors will be spread out like this. And the important thing to notice is that in that case they form a parallelogram. But if there's no inverse, then these images get pushed together, and so the parallelogram collapses. But how can we distinguish between these two cases? What we do is to look at the area of the parallelogram. And it turns out that this area is AD minus BC. Well, how do we get that? The image of the first basis vector is AC, and the image of the second is BD. This is the parallelogram, and this distance is A. This is C, and D, and B. We can find the area of this rectangle is AD. Let's move part of the rectangle around. Now we've coloured in the parallelogram and some more besides. But if we take away the small rectangle BC, we're left with just the parallelogram. So its area is AD minus BC. Well, this number AD minus BC is so important that we give it a special name. It's called the determinant of the matrix. So if there's no inverse, then this determinant is 0. Well, we can also look at this algebraically. Supposing we've got a matrix which does have an inverse, then in fact we can write down this inverse straight away. It's this. Don't worry if it looks a little complicated. The important thing to notice is that each of these 4 terms is a fraction, and in each case the denominator is just this determinant AD minus BC. And that, of course, tells us why there's no inverse when this determinant is 0. So algebraically, as well as geometrically, we can tell when a matrix has an inverse. We do it just by looking at the determinant AD minus BC.
So now we've got a way of telling whether a 2x2 matrix has got an inverse or not. You just look at its determinant. So it makes sense now to ask the question whether the set of all invertible 2x2 matrices might form a group. And so we can just quickly go through the group axioms again to check that out. Inverses, well, we've now got rid of all these nasties like this because we're only considering matrices that have inverses. Identity, that's certainly got an inverse. Associativity, that is a property that applies to matrix multiplication in general. It doesn't matter what set of matrices you're considering. Closure is the only one which really causes a little bit of pause for thought, because what we're asking there is if we have a matrix P which is invertible and a matrix Q which is invertible, do we know that the product PQ will also be invertible so that we've got a closure? Well, that does require just a little bit of thought, and you might like to try that after the program for yourself. If you get stuck, it doesn't matter because we've written it out in the text. Well, just think for a moment what we've been doing. First of all, we considered the symmetries of the triangle, and we were able to use those to get a set of matrices which formed a group. And that's quite an important idea, because very often throughout the rest of this course, you'll see quite a lot of examples of matrix groups.